In this video, we look at motion in a horizontal circle for the Unit 3 of the WJC Further Mathematics specification. We need to be able to understand and use the motion of a particle in a horizontal circle with angular speed. If a particle of mass m is moving in a circle of radius r meters with constant angular speed omega radians per second, then the speed of the particle is given by r times omega, and the velocity of the particle will be tangential to the circle. The particle will have an acceleration of magnitude a, where a is given by either omega squared r or v squared over r, and the acceleration is directed towards the centre of the circle. For most problems that you'll encounter in terms of horizontal circular motion questions, you'll find the following strategy will be useful. First of all, draw a clear force diagram for the problem. Mark on the acceleration of omega squared r or v squared over r acting towards the centre of the circle. You may need to draw a second diagram to deal with the geometry or trigonometry of the circular motion and to calculate any required angles or lengths. And then in terms of the mechanics, you'll need to apply Newton's second law in two directions. First of all, vertically, remembering that if the particle is moving in a horizontal circle, then there will be no acceleration vertically, so the resultant force vertically must be equal to 0. And apply Newton's second law towards the centre of the circle. So the resultant force towards the centre of the circle will equal a mass times the acceleration towards the centre of the circle. So we move rapidly on and have a look at 2 or 3 examples. So for our first example, we have a hollow cone of base radius 3 meters, height 4 meters, which is fixed with its axis vertical and the vertex V pointing downwards. Particle P of mass m kilograms moves in the horizontal circle with centre C on the smooth inner surface of the cone with a speed of root 8g over 3 meters per second, where g is acceleration due to gravity. And we've got 2 things to do. We've first of all got to show that the normal reaction of the surface on the cone is 5 mg over 3 newtons, and we've then also got to calculate the length of Cp and hence determine the height of C above V. So we'll start off by just drawing a diagram quickly to deal with the trigonometry and geometry of the situation. So the height of the cone is 4 meters. The radius of the cone is 3 meters. So the angle theta that we've got there satisfies tan theta equals 3/4. And Pythagoras also gives us our hypotenuse of 5 meters, so that we know that we've got sine theta must be equal 3/5 and cos theta must equal 4/5. Okay, so we'll start adding the forces and the acceleration acting on P. We've got a force, the weight of P is mg vertically downwards. We'll have the normal reaction from the surface of the cone acting at right angles to the surface of the cone. So there we've got our normal reaction, R. And we need to add the acceleration acting towards the centre of the circle of v squared over little r. Now, there's a couple of things to notice here. First of all, in the question I've been told about the speed of the particle as it's going around in this circle, so it makes more sense to use the v squared over r format for the acceleration rather than the omega squared r format for the acceleration. Secondly, need to make sure that I don't confuse the radius of the motion with the reaction force. So having used big R to symbolise the reaction force between the particle and the surface of the cone, I'm going to use little r for the radius of the motion. We're going to start the mechanics part of the question by resolving vertically. Now, if I'm going to resolve vertically, I'm going to have to resolve the force R, which means that I could do with finding the angle that the force R makes either with the vertical or with the horizontal. So, if we have a look at the diagram that we've got, we can see, looking at the triangle formed by C, P and V, that the angle CPV must be 90 minus theta. We know that the reaction force R is at right angles to the surface of the cone, and therefore the angle that R, the reaction force, makes with CP must be theta. So we can now resolve vertically and apply Newton's second law vertically. So we've got the vertical part of R, which is R sine theta, minus mg must equal naught, because there is no acceleration vertically. We know that sine theta is 3/5, so we've got 3/5 R minus mg equals naught, so R must equal 5/3 mg, which is the first part of the question done. Now, the second thing we should be looking to do with the circular motion question is apply Newton's second law towards the centre of the circle. So in this case, we're going to be applying Newton's second law horizontally to the left. The only force that gives us anything there at all is the component of R to the left, which is R cos theta. And we've got R cos theta must equal the mass times v squared over little r. We know that r is 5/3 mg, so we've got 5/3 mg times by cos theta, which is 4/5, must equal m times the speed of the particle squared, which is 8g/3, divided by little r. That simplifies to 4/3 mg on the left-hand side equals 8/3 mgr on the right-hand side. And if we simplify that right down, that gives me r must be 2 meters. So we've now found that the radius of the motion, in other words, the distance CP, is 2 meters. So if we know that the distance CP is 2 meters, and we're trying to find the height of C above V, then we have got 2 divided by h is tan theta, but we already know that tan theta is 3/4. So we've got h is 8/3 meters. Let's now move on to a second example. We've got an athlete is cycling at a constant speed v meters per second in a horizontal circle of radius 40 meters on a track that is banked at an angle of 30 degrees to the horizontal. The combined mass of the bicycle and the athlete is 60 kilograms, and the coefficient of friction between the bicycle tyres and the track is 1/4. Find correct to 3 significant figures the greatest possible value of V. So again, we need to start with the diagram, and straight away you'll notice that I'm going to treat the cycle and the athlete as a single object, and we're treating it as a particle, so we don't need to worry about the size of it at all. Okay, the cyclist is going round a circular track of radius 40 meters. And we're trying to find the maximum speed, so we'll put the maximum speed being v meters per second. We've got a weight of 60g. And we've got a normal reaction, which is perpendicular to the slope. And again, we'll call that R. And then there's going to be a frictional force. Now, if the bike is going really fast, then the tendency for the bike will be to slip out of the circle. So the frictional force will be opposing that tendency, and the frictional force will be acting down the slope. So there's my frictional force F. So we've got the forces acting on the particle on the diagram, and we finally need to add the acceleration, and again in this question we'll use the v²/r format because the question is asking us for the greatest possible speed. So we've got acceleration of v²/r towards the centre of the circle. Okay, a little bit of trigonometry to be done. The angle between the slope and the horizontal is 30 degrees. So the angle between the reaction and the horizontal will be 60 degrees. So we can now start to apply Newton's second law, and in the first case we'll apply Newton's second law vertically. We've got the vertical component of R, which is R sine 60 upwards. We've also got a vertical component of F, which is going to be F sine 30 downwards. That's going to be minus F sine 30 minus 60g. So that's the component, that's the weight, and that must equal 0 because the cyclist is travelling in a horizontal circle and there's no acceleration vertically. Because we've got the cyclist going around at maximum speed, it means the friction is limiting, so the friction must be mu times r, and we're told that the coefficient of friction is 1/4. So the equation we've just written down can be rewritten as r sine 60 minus 1/4 r sine 30 must equal 588. In other words, we've got 0.7410 times r equals 588, or r is 793.5 newtons. We need to apply Newton's second law towards the centre of the circle. So that's applying Newton's second law horizontally to the right. We've got the component of r is going to be r cos 60. The component of f, also acting to the right, is going to be f cos 30. Must equal the mass times the acceleration. So that is m times by v squared divided by the radius of the motion. So we've got r cos 60 plus a quarter r. That's because we know that f is a quarter r times cos 30 equals 60 times by v squared divided by 40. We already know that r is 793.5. So the left-hand side becomes 568.5 equals 1.5 v squared. And if we divide by 1.5 and then square root, we obtain a maximum possible value of v of 19.5 meters per second. And as we've already commented earlier on, we have assumed that the bicycle and the cyclist can be treated as a single particle. Our final example, we have a string of length 32A, has a smooth ring of mass m threaded onto it, and is fixed to 2 points A and B, with AB 24A and A vertically above B. The B is made to rotate about B in a horizontal circle. We've got to find the radius of the motion, and we've also got to find the tension in the string and the angular speed of the ring. Okay, so there's our diagram. And the first thing we're being asked to do is to consider the geometry of the situation. So we've got our distance AB is 24A. We don't know what the radius of the motion is, so let's put that in as being r. We do know the length of the string altogether is 32A, so the hypotenuse of our triangle must be 32A take away r. If we apply Pythagoras' theorem, we've got 32A minus r all squared must equal 24A squared plus r squared. Multiply the brackets out, we've got 1024A squared minus 64AR plus r squared must equal 576A squared plus r squared, which simplifies to 448A squared equals 64AR. So r must be 7A. So here's the diagram drawn again, and we're going to need just to work with the angles a little bit. So if we call theta the angle that the string joining A to the ring makes with the vertical, then we've clearly got that sine theta is 7A divided by 25A, which is 7/25, and cos theta is 24A divided by 25A, which is 24/25. We can add the forces and the accelerations acting on the ring onto the diagram now. So we've got the weight of the ring, mg, acting vertically downwards. We've got the tension in the string linking the ring to A, acting up the string. We've got tension T there. And we've also got the tension in the string linking the ring to B. And because the string just passes through this smooth ring, this tension will be the same as T. And the final thing to add to the diagram is the acceleration towards the centre of the circle. And this time, because we're being asked to consider the angular speed of the ring in the question, we'll use the omega squared r format for the acceleration of the ring towards the centre of the circle. Okay, so we now need to apply Newton's second law. The angle that the string AP, A to the ring, makes with the vertical is theta. So, resolving vertically, the component of T on the piece of the string linking A to the ring is going to be T cos theta. We've got minus mg, that's the weight acting downwards, and the T that's acting from the ring towards B has no vertical component, so we can ignore that bit. The ring is moving in a horizontal circle around B, so there is no vertical acceleration, so the resultant force acting on the ring vertically must equal naught. So we've got 24/25 T must be the same thing as mg. In other words, T must be 25/24 mg. Applying Newton's second law horizontally towards the centre of the motion, so in this case that's to the left, we have the component of the tension in the string joining A to the ring in the horizontal direction is going to be T sine theta, together with the horizontal force T, which is acting on the string which links the ring to B. So we've got plus T. The weight is acting vertically, so that doesn't contribute anything to the horizontal equation. So we've got T sine theta plus T is the resultant force acting to the left horizontally, must equal m omega squared r, the mass times the acceleration. We know that sine theta is 7/25, so we have 7/25 T plus T equals m omega squared times 7a. So that is 32/25 times T equals m omega squared 7 times 7a. But we know that T is 25/24 of mg. So we've got 32/25 of 25/24 mg must equal m omega squared 7a. Which ends up giving me omega squared is 4g over 21a. So omega is the square root of 4g over 21a. Our final example has a ring of mass 0.6 kilograms fixed to a point P on a string AB of length 1.4 meters, where A to P is 0.8 meters. The ends A and B are fixed to 2 points 1 meter apart in a vertical line, with A being above B. The ring is made to travel in a horizontal circle with angular speed omega radians per second in such a way that both portions of the string are taut. We have to show that angle APB is a right angle, calculate the radius of the motion, and then find the tension in each string and find the smallest possible value of omega for the motion to be possible. So we need to picture the situation. So there's my floor and my ceiling, if you like, for the motion. we have A to P is 0.8 meters, and we have B to P is 0.6 meters because the total length of the string is 1.4 meters. We know that A to B is 1 meter, and since we've got 1 squared equals 0.8 squared plus 0.6 squared, that certainly means that the triangle APB is a right angle triangle with the right angle being at P. That's the converse of Pythagoras' theorem. Introducing the angle theta now, we know that cos theta is going to be 0.8 and sine theta is going to be 0.6. We want to try and find the radius of the motion. Well, there's a circle. The radius of the motion then is there, and if we look at the triangle formed by the centre of the circle, A and P, then we see that R must be equal to 0.8 times sine theta, which is 0.48 meters. So, there's our diagram again, and we're now going to add our forces and accelerations onto this diagram. So, forces acting on P to begin with. We've got the weight of 0.3 G. We've got a tension in the string joining A to P. Call that tension T. There's also going to be a tension in the string joining P to B. Now in this case here, the string is attached to the ring P. And that means there's no reason at all why the tension in the upper part of the string should be the same as the tension in the lower part of the string. There's no reason at all why those two should be the same. So we've got to call the tension in the lower part of the string something different from T. So we'll call it S. And we've got our acceleration to put on towards the centre of the circle. And because we're interested in the angular velocity of the motion, then we'll put the acceleration in its omega squared r format. To help with the resolving of forces, we'll just add one or two more angles to this diagram. First of all, we know that the angle that the string AP makes with the vertical is theta. And therefore, the angle that we have between AP and the horizontal will be 90 minus theta. We know the angle at P made by the two strings is 90 degrees. So we can deduce that the angle between BP and the horizontal must also be theta. Just take a moment or two to make sure you can convince yourselves about these angle facts. We can now resolve vertically. We've got the vertical component of T is T cos theta upwards. The vertical component of S is S sine theta downwards. So that's minus S sine theta minus 0.3 G is the resultant force vertically. But P is moving in a horizontal circle, so there's no acceleration vertically, so the resultant force vertically must equal 0. So we have 0.8T minus 0.6S must equal 0.3G. If we apply Newton's second law horizontally towards the centre of the motion, so that's horizontally to the left in our diagram, then we obtain the horizontal component of t, which is going to be t sine theta, together with the horizontal component of s, which is also acting to the left, so that's going to be s cos theta, must equal the mass times the acceleration, which is m omega squared r. So we've got 0.6t plus 0.8s must be 0.144 omega squared. So we now have a pair of simultaneous equations for the motion. So if we take those two simultaneous equations, if we multiply the first one by 0.8 and multiply the second one by 0.6, then and add the two results, then the t terms will combine just to give me 1t, because that's 0.64t plus 0.36t. The s terms will cancel each other out, so we'll end up getting t equals 0.8 times 0.3g, which is 0.24g, together with 0.6 times 0.144 omega squared, which is 0.0864 omega squared. We now do a similar trick to eliminate the t's from the two equations. So if we multiply the second equation by 0.8 and subtract the first equation multiplied by 0.6, then the t's will cancel each other out. We'll be left with 0.64s take away minus 0.36s, so in other words we've got 1s, equals 0.1152 omega squared, so that comes from 0.8 times by 0.144 omega squared, take away 0.6 times by 0.3g, which is 0.18g. So we've now achieved the point of calculating in terms of omega and g the tension in each portion of the string. What's the smallest possible value of omega for the motion to be possible as described? Well, there's a risk, and the risk is that the bottom string may go slack. We need s to be bigger than 0. So we certainly need s to be non-negative. So we need 0.1152 omega squared minus 0.18g to be greater than or equal to 0. So that gives me omega squared must be greater than or equal to 15.31, or omega must be at least 3.913 radians per second. As omega increases, t will get bigger and bigger, and eventually the tension will get too big and the string will break. So in fact there must also be a maximum possible value for omega, but we can't determine that because we don't know what the maximum possible value for t is.